Hello everybody and welcome back. It's been a good time since we launched our first machine learning challenge about predictive maintenance. So in this opportunity we are going to know who won the competition as well as the solution of the problem. Now if we take a look on the records of the challenge, we can see how well our participants did it on the leaderboard. And we are glad to say that although this was the first time in our sectional contest like this was held, they really showed great skills and a very competitive performance, being the bars in this graph the number of submissions per day, and the red line the shipped scores during the contest. Now let's meet the winners in a quick presentation that we have prepared. Okay, in third place we have the Mars team, formed by Carlos Avila, Marco Castro and Jorge Delgado. In the second place we have the ACS machine learning team, formed by David Arias, Carlos Carrillo and Brian Salazar. And finally, in the first place we have the Besta team, formed by Diego Gomán, Ivanova Jumbo and Kevin Silva. This is a short description of the selected models by the winning teams, being 2 ensemble algorithms and 1 neural network architecture, the isolation forest by Besta, the random forest classifier by Mars, and the neural network by the ACS team. You can check the entire workflows in our GitLab repository as well as the notebook that we are going to present. So this is the workflows that we propose, starting from 2 key steps. First, the data structuring, and second, the strategy to handle the data imbalance. Then, as usual, we have the outlier removal, the missing value imputation, the model building, and finally the criteria to select the date of a predicted failure event. Now let's see why data structuring was so important for this challenge. As you can see, we have more than 20 CSV files with information of the electrical behavior of the pump as well as the production rates. So our first task was to figure out the proper way to merge these files in a single data frame, discarding the conventional methods because of the disproportion between the high frequency and the production data. Then, once we merge the raw data, we find a huge imbalance between the number of observations and the failure events. So, to better explain the cause of this problem, we have to check the telemetry frequency, which is 1 record every 20 minutes, resulting in a really big dataset with a relatively small number of disruptive events within a period of 2 years. That's why we have changed the former frequency to reduce the effects of this imbalance to 1 record per day, giving us now 59,000 observations instead of 8 million, which is certainly a turning point for the solution of this problem. After that, we can proceed with the outlier removal, the missing value imputation, and the model selection, which is a multi-layer perceptron with 3 hidden layers, not a complex architecture as you can see. Nevertheless, it works pretty well if we consider the multi-class weights for the classification. Now, let's explain some results using the selection criteria. We've noticed that the neural network learns well to classify the failure events in 2 scenarios. One related with an anomaly behavior of the vibration readings, which is the green line in this plot, and this new line, the failure event. On the other hand, the neural network has learned to classify the failure event based on the steep drop of the other parameters, as you can see in this plot. That's everything about the presentation. Now let's take a look on the notebook. Okay, so this is the data structuring procedure that you already know from previous videos, and this is the class that I have defined to change the frequency of data. Later we have the analysis of the distributions, the outlier removal procedure, and very important, the missing value imputation, where I have defined this function to fill the nonce using an ensemble algorithm instead of the backward and forward fill methods from pandas. Then we have the model selection, where we defined the class weights by using sklearn. Then we do the data splitting, and here we defined the number of layers and the hyperparameters to train the multi-layer perceptron. After this, we get the prediction for each one of these wells, either yes or manual off. Finally, for the selection of the predicted date, I have defined two functions, one to plot the behavior of the curves, and the other to choose the predicted date either by vibration anomalies or by the steep drop of the other parameters. Now you can see the MLP does the job pretty well with the vibration anomalies and the drop behavior of the curves. Nevertheless, precision may differ based on the quality of the data in wells like this, where most of the values are close to zero during the whole year. A good way to solve this problem would be to use the information of the nearest neighbors to treat this data. Now let's go ahead and let's concatenate all these results in a single data frame to be scored. And here we go, this is our final result to be compared with the real output of each one of these wells. Now notice that our score metric has penalties based on how far the prediction is from the real date, being -3 the highest penalty for predictions with more than 30 days of difference. Finally, this is our result for each one of the testing wells, and this will be the final score for this workflow. Okay, that will be everything to share about the solution of this challenge organized by the SPE Ecuador section. Keep in mind that there are still some other tools that we can use to improve the accuracy like cross-validation, but that will be something to do for future opportunities. We hope you have learned and enjoyed from this challenge. It was a big experience for us to hold a contest like this, and for future opportunities we will be glad to see you there as well. My name is Felix Gallo, and it was very nice for me to share this time with you. Take care and bye bye.